can you see this screen? Can you see my screen? Hello. Wait, guys, you're not dead, right? You can see my screen, right? Just like, I don't know, unmute and say. We can see the screen, right? Oh, cannot see screen. Oh wait, sorry, give me a bit. Okay. Hello. So welcome back to elementary, day 3. So I guess we're going to go through the editorial today for the contest. But I don't know if you can see my screen though. So can you see the screen now? It was black before, but I don't know if it is black now. Oh my god. Oh, it's not streaming on YouTube, huh? Sorry, just give me like 2 minutes. I think there's something wrong with the YouTube stream. Yeah, I'll just like sort it out and come back. Okay, okay, I think it should be fixed on YouTube. If someone's on the YouTube stream, right, are you able to see my screen? Okay, that's great. Hi that guy. Okay, so I guess we'll just go on with the editorial then. Sorry for the delay. It's a bit of technical difficulties. Alright. So welcome back to elementary and welcome back to day 3 of Novcourse. Today we'll be going through the data structures contest editorial from today's morning contest. So yeah, the concepts, the first question was stack, the second question was map. But you should use an unordered map because it's faster, like much faster. The third one is priority queue. The fourth one is also priority queue. Alright, here's the scoreboard, but like the scoreboard is kind of scam because like half the FCs are like trainers. So like yeah, the scoreboard is kind of scam lah. Okay, let's go on to the problems. First one, bracket EX. You are given a sequence of bracket characters. Find if the sequence is valid or invalid. A sequence is valid if the brackets match. Alright, so here's one thing to note, right? This sequence, oh my god, whoops. So like this sequence here is not valid because the closed square bracket, the fourth character, like this one here, it is not corresponding to this one. This fourth character is actually corresponding to this third character over here, which is obviously wrong lah. So any closed bracket in the sequence will correspond to the nearest open bracket to its left. As you can see, the square bracket, it doesn't correspond to this one, it's this one. So you should use a stack lah to keep track of this. When you encounter an open bracket, just push it into the stack. When you encounter a closed bracket like this, if the stack is empty, or the top of the stack does not correctly correspond to a closed bracket, the sequence is immediately invalid, and you can just straight away print invalid. So like, let's just assume, right, in that string of brackets they gave you, the first one is actually a closed bracket. If the first one is a closed bracket, right, there's no way you're going to be able to solve this bracket in a sense, right? It's impossible to solve this if this is going to be the first character in the string. So if the stack is empty and if you find this, it is immediately out. Likewise, if the top of the stack is a square bracket, like this open square bracket for example, and the next character in the string is this curly bracket, it's not going to work because this curly bracket does not match with this square bracket here. So your sequence is once again invalid. So notice that the stack only stores the open brackets we encountered so far, because if you just encounter an open bracket, you just simply push it inside, because it's like a new problem. If you get what I mean, it's a new problem. So if you encounter a pair of brackets that correspond to each other, like the top of the stack is this square bracket and the next character is this square bracket, congratulations, you can pop out that. You can just pop the stack and remove this open bracket. So therefore, the sequence is valid if the stack at the end of at the end of the string, if the stack is empty, then the sequence is valid, and if it is actually valid now. So if you look through this code here, right, what I do is that if the stack is empty, if the character is a closed bracket like this, then you know it's false. Then you know it's already invalid now. So you just set this boolean flag to false, and you just break, because there's no point of going through, because you already know the sequence is invalid. Else, if it's an open bracket, just push it inside. And if the this one is if the stack is empty, but most of the time the stack is not going to be empty, right? So if you look through this, so this condition, if the current character is a closed bracket, then you gotta compare to the top of the stack. If it corresponds, that's what this very long conditional means, then you just pop the top of the stack, because you have solved that open bracket. Else that means the brackets do not correspond, and that means your sequence is straight away invalid. So just like this one, you set pause to false and you break. Okay, so that's only if, oh my god, what's that? Okay, that's only if it's like this. Else, if it's an open bracket, just push it normally. Yeah. So if you go down here, if the stack, at the end of everything, if the stack is empty and pause was not set to false, then your sequence is valid, or else it is invalid. Yeah. So that's how you solve the problem. Any questions about this? Oh, zoomed in. Apparently it's too zoomed. Okay, never mind. I'll just put it this way. Okay, next. Good sequence. So the bridge statement is that you're given a sequence of positive integers. A good sequence is when for each number ai in that sequence, that number appears like that same number of times in the sequence. So what is the minimum number of elements you need to remove to make that sequence a good sequence? That's what you need to print out. Alright, so here's an observation that you need to make to solve the problem. Also, let me just go in there. It's kind of easier for me to show. Yeah. Shit. I see. Okay. There we go. We have this. Alright, so for each number in the sequence, right, let's just call that x for any number in the sequence. If x appears more than n times in the sequence, sorry, if appears more than x times in the sequence, sorry, the only way to make the sequence good is to remove the excess appearances of x until x equals the number of times x appears. So for example, right, look at the first test case here. We have 4 trees, but then we need to have 3 trees for it to be a good sequence. So you gotta remove like 1 tree so that we have 3 trees so that the sequence is good. So that's one case. That's if x appears more than x times in the sequence. But what if x appears less than x times? The only way to make the sequence good is to remove all instances of x. You just cannot, because you can't add numbers into a sequence, right? This question only allows you to remove numbers, not add numbers. So you have to remove x. So if you look at this, for example, the sample input 2, we have 2 2s, 2 4s, and 1 1. The 2s and 1s are correct, but like look at 4. There are only 2 4s. You can't add 2 4s because for this to be a good sequence, you must have 4 4s, right? So you should just remove the 4s. You have to remove the 4s. So remove everything. So the good sequence will be 2 1 2. Also note that an empty sequence is also a good sequence. So yeah, just remember that. So we go here. How to count the number of times each number appears in the sequence? Use a map. Actually use an unordered map, but don't use a map. Unordered map is faster. The key is a number and the value is the number of times you encounter the set number. So you define it like this. But actually I'll just do this. Okay, because this is the editorial, might as well just put it in. Yeah, unordered map, okay. It's faster that way. Oh my god, I can't spell. I failed English. Okay. Yeah. So yeah, you define the map like this, and for when you iterate through the array that they give you in the input, just increase the number by 1 but like this. Then, like I said, the key is the number you just encounter. So once you finish iterating through the array, then you iterate through the map you just created, and you do what we described in this previous slide, in this slide. The answer is the number of numbers you got to remove in total. So let me just go through the code now. You input n, yeah, that's pretty obvious. Then there's the array. You input each number in the array, which is like these things here. And then using that x as using the x as the key, you increment it by 1. Once you do that, you have a variable called answer, which is basically what you're gonna output. And this is how you iterate through a map. From auto it, like it is just a variable, just like I, equals to mp.begin. So we start at the beginning of the map. Then while the iterator is not at mp.end, we just keep on like going forward. So that's what this line of code here means, 25. So in maps, right, they actually store as key value pairs, right? So therefore, whenever you iterate through a map, your IT is going to be a pointer to a pair. So the first element in the pair is the key. The second element in the pair is the value. So to make it easier for you to code and to make your life easier, just set it as variables. Key equals to it, the first element of it. Now notice I didn't use it dot first. I used it arrow first. It's actually hyphen and the greater than symbol. This is the same as asterisk it, and then you bracket the entire thing and then put dot first. It's the same thing because we need to dereference it, and then we got to access the first of the pair. So this is a much easier way to do it. Just put it arrow first. This one you only use this when you need to dereference a pointer. That's when you use this arrow symbol. So if the value is smaller than the key, this means that x appears less than x number of times. That's what it means. Then the answer is incremented by x itself. Because like I said, if x appears less than the number of x times, then you have to remove all instances of it. Else, you increase answer by the difference between the value and the key. This is when there's more x then this is when x appears more than x times in the array. So therefore you just need to decrease the excess x in the array. So you just do it this way. You just increase answer by the difference between value and key. Once you do that, simply print answer. Any questions about this? Okay, so if not, wait, okay, I think the YouTube stream is still a bit screwed. I think something to do with my Zoom settings. Just give me a bit. I'll just like. Wait, sorry, give me a bit. I'll just like fix the YouTube stream. No wonder. Wait, okay. Okay. I think I fixed the problem with the YouTube stream. I did not see that. So sorry. Okay. Okay. I hope the YouTube stream should be fixed. I hope you can see my entire screen now. For those who were just looking at the YouTube screen, it was kind of screwed. So yeah. Okay. Next question, vertically challenged. You are given a sequence of numbers. For each I from k to n, print the kth largest number between indices 1 and k. That's basically what the entire fluff means. I'll just go to the problem itself. So yeah, so like Zane thinks the optimal height among a group of girlfriends of size at least k is the kth shortest. In this case, like the one with the kth largest rank. For each I from k to n, Zane wants to know the optimal rank of the first I girlfriends of the row. So I mean, like, okay, that's all like kind of annoying. It's kind of like confusing. This one is basically the key of the problem statement. This output basically tells you what you need to like actually print. This is actually meant to distract you. Output for each I from k to n, output the kth largest rank among the first I girlfriends, separated by new lines. So that means you just have to iterate through a list to get all of this. For each I from k to n, you print the kth largest number between indices 1 and I. Oh, I think I put it wrong. Oops. Yeah, I'm so sorry. Yeah. Indices 1 and I, not 1 and k. So print the kth largest number that you have encountered so far. That's what it means. So here's another observation. Between indices 1 and k, the kth largest number will be the smallest number you have encountered so far. So let's suppose k equals to 5, and you have gone through index 1 to 5 in the sequence they gave you. Like for example, this one. Let's just say you came here and you went through the first 5 numbers. Let's say you came here already. You already went through the first 5 numbers. Okay, this array isn't the same as that one. So let's just assume it was like this. Let's say we sorted the first 5 numbers when k equals to 5. So you will get something like this. The kth largest, aka the 5th largest, is number 2, because it's the smallest of the 5 numbers you have gone through so far. So between indices 1 and k, the kth largest number will be the smallest number. So once you have established that, let's add in a 6th number. Let's say that the 6th number was 4. Now 4 is larger than the previous kth largest number 2. It's larger than the 5th largest number. So what happens is that 4 is basically like the 4th largest number in the sequence now. So when you add 4, it pushes 3 and 2 down the order. So 3 becomes the new 5th largest element. 2 gets dislodged, as you can see from this graphic here. You put 4 here, now 3 becomes the 5th largest element, and 2 becomes the 6th largest element, and therefore this 2 will never ever become the kth largest element again. It will only be at least 6th largest. And that's one important thing to know. Know that for all numbers here, right, if they start off like, no matter all these numbers here, right, they cannot move to the right. They will only move to the left. So that means the kth largest number, right, throughout, so as you process the array from k to n, the kth largest number will always increase, it will never decrease. And you can actually see that from the sample test case here. Notice something here, right? 2, 3, 3, 5, 6, 7, 7. The numbers never decrease, they only stay the same or they increase. So from this and from this, you can therefore deduce that adding in larger numbers will only push the kth largest number, like will only like change the kth largest number. So what if we push in a smaller number, like 1? If you push in 1, right, since it is not bigger than like the top 5 elements, it's going to be the 6th largest element, and therefore it's not going to do anything to the top 5 elements. There's no change here whatsoever. So what we can conclude is that if you add anything that's smaller than the kth largest element, there's going to be no change to the top k elements. So this slide is probably the most important. This slide gives you the hint. So therefore, how should we solve this? Other slides here. If the next element is larger than the kth largest element, the kth largest element will change, and that's certain. If the next element is smaller than the kth largest element, nothing will happen. These two sentences are key. So therefore, use a priority queue to maintain the smallest element in the k largest elements you have come across the array. That means you have to define it like this. Don't use priority queue int only. You have to do it this way. By doing this, the priority queue will pq.top will give you the smallest element instead of the largest element. Because by right, as you may recall, pq.top should by right give you the largest element. But this reverses the way it is sorted. So iterate through the entire list from index 1 to n. Before you reach the kth element, push each element you encounter into the priority queue. And do not care about whether it's large or small or anything. That doesn't matter. So for each element from indices k plus 1 to n, and one more thing, this is one index, okay? This is not 0 index. In case some of you are confused, it's not 0 index. So yeah, it's one index. If the element is smaller than the pq.top, aka it is smaller than the kth largest element, then do nothing. So it's basically this case. If the element is greater than or equal to pq.top, pop the kth largest element, and just pq.top, pop the kth largest element, because it will definitely change. It's this case that we're talking about. And push the new element into the priority queue, as the new element, because it is bigger than the kth largest element, it is certainly among the k largest elements you have encountered thus far. At the end of both cases, print pq.top. So here's the code again. So once again, this one is to read the input. We get the vector inside. I just use the vector. We get the input. So here's priority queue. So here's the priority queue. From I equals 0, I smaller than k. These are the first k elements, the first k elements. Just push it inside the priority queue with no care. Then print the pq.top. This is the kth largest element after processing the first k elements. Then for remaining elements, if the new element that you discover is smaller than pq.top, it doesn't do anything to the priority queue and print pq.top. Or else, just pop the top of the priority queue, push the new element inside because it is larger than the kth largest element, and then print whatever is the pq.top, because the pq.top is always the kth largest element. That's how the priority queue works. Alright, any questions? Okay, if not, then let's go on to the final problem. So potatoes queues. So like customers are buying stuff. Each customer has an ID number and processing time T. We manage these people in a special queue. There are two operations. Join ID T, a new customer with ID number ID and processing time T joins the queue, and the operation serve is the customer with the lowest processing time in the queue is served. So that's the thing. The whole point is whoever has the lowest processing time in the queue is the one that's going to be served. But you know something? The problem statement actually gave a hint. Look at this. It says like this queue is special as it will prioritize the people who have orders with shorter processing times. See? Priority queue. It gave you the answer. The problem statement literally gave you the answer. So yeah, the answer is actually a priority queue. So we use a priority queue to maintain the customer with the smallest processing time. This time, you gotta print the customer's ID, not the processing time. So you need to tag that with the processing timer. So how are you gonna go about it? Since the priority queue is meant to sort by processing time, you use the pair data structure. Use pair int. The first number is the processing time, and the PQ will sort by this. The second is the ID number. The second number is ID number. So your priority queue should be defined like this. This very long line of code, but it's actually very unnecessary. So instead of writing it like this, at the top of your code, just write this. Actually, I don't know if they went through this like on Friday because I wasn't there, but basically use this type def statement. It basically shortens this to this. So now you can write pi instead of pair int. And look at this, it's so much neater now. See, so much neater. And again, remember to use vector pi greater pi, because once again we're sorting from smallest to largest, not from largest to smallest. And just a note, and this is quite important, in a priority queue of pairs, the pairs are sorted by the first element only. The second element is used as a tiebreaker. So remember that. Iterate through the operations. This is how we go about solving the problem. If it is a join operation, push a pair of the processing time first, then the ID. And that's important, because if you look at the problem, right, the input is the ID number first, then the processing time. But this is wrong, because remember the PQ sorts by the first element, and the first element should therefore be the processing time. So processing time first, then the ID. If it is a serve operation, print the second element of the top of the PQ, aka pq.top.second. Print this, and remember to pop the top element using pq.pop. So here's the code. N, yeah, we see in N. This is the priority queue. This is how we declare it. This is how we initialize it. The string. This one is the operation. If st equals to join, meaning it's a join operation, we see in the other two numbers, the ID number and the processing time. And instead of using xy, we put y comma x, because y is the processing time. And we push this pair into the priority queue. Oops. Else that means the operation is a serve operation. You print pq.top.second, and you must pop the element because the guy is served, right? He was not in the queue anymore. And yeah, that's it for the editorial. Do you have any questions? If you have any questions, feel free to ask in the questions chat, or just like DM any of the trainers. We'll be happy to help. Okay. If not, right, let's get into the actual lesson for today.
Wait, do you want to do DS1 Kahoot first?
Oh right, yeah, I forgot the Kahoot existed. Okay, yeah, let's do that. Okay, so
Okay.
we prepared a Kahoot for you. Or rather, Jerome prepared the Kahoot. This guy hard carried the Kahoot, so thank him.
Yeah, cause I'm that good, you know.
Yeah, you're very that good. Okay.
Wow.
We just. Oh wait. Jerome, I think you need to share your screen, cause like.
Yeah. I'll share.
Okay, just give me a minute.
Okay. This Kahoot If you attended last lesson, it's the same, but I added more questions and I changed some of them also. Oh wow, okay, sure. Okay, I actually don't mind if the trainers join. It'll be a bit more fun, I guess.
Okay. Also, that wasn't me, you know.
Oh, on God. Damn. Okay, I'm gonna start it now. Okay, alright. Okay, yeah. So this question is which DS automatically sorts elements. So it sets maps and priority queues. Vectors do not sort elements automatically. Okay, so which operations can be used on queues? Operation means the one with like the dot in front of it. Okay, yeah. So dot push and dot size are both correct. The reason why queues don't use dot push back is because you can only push in elements to the back. So like you don't need to specify that it's at the back. And you can only pop elements from the front. So you also don't really need to specify that it's from the front. Okay, so which DS uses a FIFO? Yeah, okay, so that's a queue. First in, first out essentially means if the obviously it's like you put an element in first, therefore it will be the first to come out. Queues are like that because when you push an element in, the element at the front will come out first also. So because of that it works based on first in, first out. Priority queue and stack don't work like that. Stack is first in, last out, and priority queue is sorted. So it's not necessarily FIFO. Okay, this is a big O notation. Yeah. Okay, so n log n is not faster than O(n), and it's a bit okay. Essentially, n times log n is always going to be faster than O times n. Wait, is that right? Yeah, I'm pretty sure that's right. So it's never n log n is not going to be faster than O(n), unless it's just O log n. Okay, yeah. So maps can store more than one data type because maps, they work like they have a key and a value. The key and value don't necessarily need to be the same data type. So the key can be a string, and the value of the key can be an integer instead. Okay, time complexity of random access in a list. Yeah. So the answer to this is actually in the slides. What this question means is if you were to pick any random element inside of a list and you wanted to ask like what is it, it would take O(n) time in order to do that. Because a list is like it's very slow and the computer, I don't think the computer stores it like an array. So every time you want to find out what an element is, you always have you have to pass through every element in the list in order to find it, I think. I'm not so sure, but if it's not, then it's still O(n) because the slides say so. Yeah.
Yeah, you say so. No, actually, yeah, it's like that. Basically, you start on the first element, and then like you keep on going to like second element, third element. If your luck is really that bad, if you're like closer to n, then yeah, it takes O(n). Worst case time complexity O(n).
Yeah, so time complexity is always worst case. Okay. Alright, so just now we already said to access any element in a list takes O(n) time, but to access any element in an array takes O(1) time. That's because the computer already knows which element is where in the array. And therefore, it's going to be faster to access anything. And we also say in C++, lists are kind of the slowest DS, so it's always going to be slower than anything. So like, don't use it. Okay, multi-set, something that we didn't really touch on. Okay, so multi-sets can't hold up to 3 of the same element. A multi-set can hold duplicates of the same element. What does that mean? It means like if you have the numbers 1, 2, 3, and then 1 again, the multi-set will have 1, 1, 2, 3, because it can hold duplicates, but it will not have 1, 1, 1, 2, 3. Yeah, so it can only have up to 2 of the same element. Okay, this is my solution to gentle pairs actually. Okay, so the option is O(n) squared. O2n plus n squared is closer to the number of operations in the code, but number of operations is not the same as number of as it's not the same as big O notation. What we're more interested in is the most dominant term. In this case, n squared is the most dominant term. And also, if you look at every one of the questions, right? Every one of the answers, only this one, green, O(n) squared, holds the most dominant term. All the other ones don't. It's like plus or for 2 times n over there. Yeah, okay, so both arrays and pairs, their sizes are fixed. Pairs can only hold 2 elements, and an array, you have to initialize how many elements it can hold before using it. So it's also got a fixed size. But vectors and DQs, both of them, you can dot push back or just dot push elements into it. So it's actually not fixed. It can go as big as you want, minus MLE. Okay, given a time complexity of O(n) factorial, what's the maximum n that can pass in 1 second? 1 second is the most common time for the time limit for CP questions. Okay, the answer is n equals 12. This answer is also in the slides. There's no real explanation for it lah. But n equals 64 is not the answer because I'm pretty sure 64 factorial is like a few quintillion or something like that, and there's no way that the computer passes that. It's actually n equals 12. Okay, brick is the question brick. So if you don't know, go and open another tab and like search for it. Yeah, this question has a very long time limit. Okay, so brick uses a stack. I don't know if you search for it or if you just guessed, but yes. Also, if you didn't know which DS it's supposed to use, you can just go to the slides. The slides will actually tell you that brick is supposed to use a stack. Okay, so this code will actually have an RTE, or it'll just be an error because sets, you cannot index on a set. So just now that question is trying to find like index 1 of set S, but that will not output anything. It will just have a runtime error. Wait, someone just sent something in the chat. Okay, Kaitin, I get it. Okay, this is also in the editorial and the slides. You need to have firstly integer, then a vector will work as like a frame to hold to like sort the elements, and then you have greater integer in order to reverse sort it. It's like a list question, but now for arrays. Alright. So to access any random element, it's in the slides also, it's just O1 time, which is why arrays are faster than lists. Yeah, so in case you forgot, a pair can only hold two elements. Unless you have pair integer and there's another pair inside, but like that doesn't count, you know. So a pair can only hold two elements, and if it can only hold two elements, that means that it can only hold two data types. Cause like, how do you have three data types with two elements, right? Okay, this is actually reference to the editorial just now. Okay, so it's p.second.first. Why is that so? Because the string, okay, the overarching pair, right, is integer and then another pair. And inside this second pair is the string as the first variable and a boolean as the second variable. So what you need to do is p.second in order to access the second pair, and then that dot first in order to access the string. It's not p.first.second because yeah, and it's also not just p.second. p.second.first with the bracket here is also wrong. That's the most chosen one. Dot second and dot first both do not have a bracket after it. Okay. So the error is called segmentation fault because you're accessing out of bounds, array out of bounds. Undefined behavior is what we call is like what happens next. Okay, good job. You win bragging rights, I guess. Okay, that's it from the Kahoot. Now I guess we have to go on to the actual lesson. Like, who's gonna take the lesson?
Yeah, Jerome, you do the lesson. Yeah, you
Man.
like half of it.
This guy, man, this guy. Okay, okay, I'll take the lesson. Okay, so y'all can see the screen, right? Yeah, just confirming.
Yeah, I can see.
Okay, so classic techniques and interactive problems. Yes. Hello. This is our agenda for today. So we'll be going through some classic techniques, including greedy, plus sorting in reverse, because like that's related. And there's also binary search. So interactive problems first. What is an interactive problem? Firstly, we have to go through what are functions. A function is a group of statements that performs a task, and it's useful for sharing code between different sections of the code and tasks that require recursion. If you don't know what recursion is, you can go and Google it. There's quite a lot of videos that explain how. If else, I think we'll also go through what recursion is later on. But in any case, yeah, just to recap, functions are quite useful if you want to declutter your code or if you're using the same kind of code all over the place. Yeah. So parts of a C++ function, there's a return. It needs to return something. Then there's the function name, the arguments inside the function, which is just the info that you pass to the function so that the function can do something with it and like return you another value, and the code inside the function. So this is what it looks like. Firstly, you say the return type is the data type of what it's gonna return, which can be it can be an integer, a string, a boolean, then the name of the function, okay, and then the arguments that you pass into it. In a C++ function, you have to remember every argument that you pass to it, you need to write the data type in front. So it cannot just be you write integer once and it assumes that every other argument you pass in will be an integer. No, you can't do that. In front of every argument, you need to write the integer. You need to write the data type. And then it does stuff, the code inside the function. Okay, yeah, remember to do the curly brackets also. You write your code and it returns the return value over here as according to the return type. If you don't want your function to return anything, you just call the return type as void. You say void over here and you don't need to return anything. Okay, so an example, integer increment. And you have one variable that you pass in, which is an integer called x. And after that, it returns x plus 1. So on the return value, you can also do arithmetic in there. And all this does is that you pass an integer into this function, and it'll return you a plus 1 value, like a value of that integer plus 1. Okay. So notes. To invoke a function, use the function name and put the arguments in the brackets after it. Example, int x equals to increment 1. So increment 1, what this does is it'll pass 1 into the function. This x here will now be 1 and it'll return 1 plus 1 equals 2. So this increment bracket 1 will equal to 2. So integer x outside here equals to 2. Do note, if you have a variable outside of your function, you can use it inside of your function, but it just cannot be inside of your main function. So for example, if you declare integer x inside of your main function, and you declare, if you declare integer x inside your main function, you cannot use integer x inside like this function here, because it won't be able to know what integer x is. But if you initialize x outside of the main function, then you can use it here. And also on another note, this integer x is not the same as the integer x over here. What do I mean by that? Okay. Over here, integer x is like inside of this function only. This integer x is somewhere else outside of the function. So x over here is not going to be the same as x over here. It won't change it. Just for you all to know. Okay. So another type of CP problem. Traditionally, you just read stuff from the input and you output your answer with cout. However, there's also another type of problem called interactive problems, which give quite a bit of flexibility. So your code can interact with the judge through function calls. What it says, the function will probably tell you like, make a function called, I don't know, A, B, C or whatever, and the judge will read that function, and by reading that function, it will interact with you. Okay. So if you want to do this, you can try minimum on Codebreaker. We can do that later, I guess. Oh yeah, that's the answer. I'm gonna show that now. Wait, should we just do it now? Do minimum now.
Yeah, I think you should.
Wait, Sriram, do we
Yeah,
just do
we
minimum
should, we
now?
should. Yeah, we should. We'll take it.
Okay, alright. Alright, so go do minimum on Codebreaker. Wait, let's just say we come back at 2:15 once you're done. Okay, it's 2:15. Can I have a raise of hands? Who has done minimum? Three people. Four people. Okay, Sriram, I get it. You're very good. Uh, sure. You know what? That's good enough for me. I'll just go through the solution, I guess. Okay. Yeah, y'all can see my screen. So this is the solution. You just have your int find min function. Make sure that this name is spelled correctly. And then you pass through an integer, and you also have an integer array called a. Then what you do is that you initialize a variable called current, shortened to cur, and it's just a really big number. This number, instead of just like looking at the sub, instead of looking at the task limits for how big the number can go, you can actually just use something called int max or ll max for long max. It'll just give you the largest possible integer that can be held in that variable. And what you do is for each element inside of the array, you compare it with the current smallest value. So what happens is on the first element, you compare current and like that first element. Most likely, okay, definitely because of the task limits, this first element is gonna be smaller than this this very big number. So current will now be equal to the first element. And from there on, you keep comparing the current smallest element. If there's one smaller than it, then your current smallest element will equal that now smallest element. And at the end of it, you return the CUR. So yeah, that's just how we do it. Next, classic techniques. So why is it so classic, right? So classic techniques are just algorithms / ideas that are quite easy to implement, which is why they're called classic. So similar to data structures, they're just a bunch of tools that you will use from time to time when solving problems. The difference is that classic techniques aren't there's no like built-in function for classic techniques, so you actually have to code it out. It's not like a data structure where you just like initialize it. Hey, so one of the most basic classic techniques is greedy. So this is a problem statement here. This problem is called lunchbox. You're the manager of a restaurant. You prepare n lunchboxes and hope to distribute them to some schools. Suppose there are m schools and assume that each school asks for this certain amount of lunchboxes. So your aim is to distribute as many lunchboxes to as many schools as possible. Moreover, you have a rule. For every school, you either give 0 or the number of lunchboxes that it needs. So that means that if a school needs this number of lunchboxes, you either give them that number of lunchboxes or you don't give them any at all. So can you make a program that can help you find the maximum number of schools that can receive lunchboxes? Okay, so we are gonna use greedy to solve this, but first, what is greedy? So greedy just means that at every step of the problem when you're solving it, you use the locally most optimal choice at each stage. So how do we be greedy? Sorting, yes. Most of the time, greedy will use sorting, and okay, just some visualization website. I don't think I need to look at it actually, but you can go look at it on your own. So what you can do is you can arrange the elements in the array in a sequential order using criteria. When we explain the algorithm to solve this in the next few slides, it's assumed that the arrays contain numbers and they're sorted in an ascending order. So how to understand sorting? Okay, this is just like different types of sorts lah. Okay, first and foremost is bubble sort. You all probably have heard of this before. So you go through the array and compare each element to the one after it. Okay, so if the element after it is smaller than this element, you switch their places. This process has okay. Then this process itself has to be done n-1 times. But why? Okay, if the biggest element is the first element in the array, it takes n-1 iterations to be quote-unquote bubbled to the right. So that's kind of why we call it bubble sort, because when you do this operation, like when you swap two elements, if they are like not in a sorted order, the bigger element, since it to be sorted, it will probably go towards the right. Therefore, when you run this algorithm, right, it looks like that bigger element is being bubbled towards the right. Okay, and the worst case time complexity for this is O(n squared). I think O(n squared) is when the array is sorted but in the reverse order. Okay, next type of sorting algorithm, merge sort. So what you do is you have an array, you split the array into two, and then for the now split array, you go into each split section and you split it into two also, and you keep doing that until the array is just split into individual elements. And you merge the arrays together and sort while doing so. What does that mean? So assume we have our array, it's split down to individual elements. You merge those elements together, and what you do is that you merge them in a sorted order. So let's say your two elements are 5 and 7. What you would do is you merge them into an array, and the array would be 5 and 7. If it was 9 and 3, you would flip the order and you merge them together to be 3 and 9. So why do we do this? It's because merge sort takes advantage of the fact that if you want to merge two sorted arrays, wait, what was it again? Okay, it is faster to merge two sorted arrays into one big sorted array as compared to have one big sorted array and sort the whole thing altogether. If you want to find the proof for that, you can also find Google. You can Google one and look on YouTube. Worst case time complexity is n times log n, log base 2n. Okay, I think we went through this already, but for those who weren't there last lesson, log is the opposite of exponential. It's the opposite of exponent. So if log base 2n equals to x, then 2 over here to the power of x equals to n. Okay, so log n comes from the amount of times that the array has to be split/combined. Because like when the 2 is because we split the array into 2. Yeah. Okay, so this is a visualization. You can watch this here. You split the array, keep splitting it until it's down to individual elements. And now you look at these two elements, 6 and 5. 5 is smaller than 6, so it goes in front. 3 and 1. 1 is smaller than 3, so it goes in front. 8 and 7. 7 is smaller, so it goes in front. And yeah, you get the point. Let's just watch this whole thing, I guess. Why not? Okay. 5 and 6. So these are two sorted arrays. Yeah, that happens. Okay. So what is it doing here? Essentially, it takes the first element of each array that it's combining. It compares it. If the first element of array A, right over here, if the first element of array A is smaller than array B, it will go first. See, 3 is smaller than 2, so 2 goes first instead. 3 is smaller than 4, so 3 goes first. 4 is smaller than 5, so 4 goes first. And yeah, so on and so forth. So if you look at that animation, you can understand what it means by the fact that merging two sorted arrays into a bigger array is faster than sorting one whole array. Okay. So there's also counting sort, maintain an array of the number of occurrences of an element. And by going through the keys in a sorted order, the keys of the element, add the key v times into the new array. And this worst case time complexity is O(n). Actually, it's O max value of array. Limitations is that the numbers themselves must be small enough to be able to be sorted as keys. And this can be done using a map, but that time complexity would actually be longer. Okay, there's a lot of other sorting algorithms also. There's shaker sort. For those who were at RIIC conf yesterday, RI students, y'all would have heard like in the background some weird sound, right? It sounds like very techno. That was actually a YouTube video of sorting algorithms working. Yeah, there's a video for it, and y'all can watch it on your own. But do we need to memorize all of these? No, actually we don't. Ha ha ha. Because in C++, there is a standard function called sort, and it will have a time complexity of O n log n. All you do is you use this function and it will sort like whatever data structure you want. Minus some. I'm not gonna go through that. Wait, did someone just say something? Okay, never mind. So yeah, you can just use this standard sort function. You don't actually have to code out a sorting algorithm. And how do we use sort? What you do is you have your data structure, you have a start pointer, an end pointer, and an optional comparator. This optional comparator can be like greater over here to sort the thing in reverse instead. So for example, you have an array, it would be array, sort array first, because the array name by itself just is a pointer to the first element. And then you have array plus 100. This one plus 100 is just how many elements are inside of the array, because this will point to the last element. And it'll sort this entire array. If it's a vector, what you do is the vector name dot begin and dot end. And then if you want to sort this in reverse, you can have greater int over here. This is like reference to the Kahoot also. Yeah, that's just that. Vectors is dot begin and dot end. And if you want to reverse an array, you can also do it this way. You don't have to use the greater comparator. You just do it like that. It's the same idea of the beginning and ending pointers. Okay, so this is the question that we were looking at on the front cover of the classic techniques. Given n lunchboxes, find the maximum number of schools you can give lunchboxes to. You can only give 0 or ki number of lunchboxes. Ki is just a specific number for each school. Okay, let's look at the proof. I think we've already done lunchboxes. Not so sure though. Okay, oh my goodness. Okay, this is just the proof lah. Let I2, I3, IGRD, greedy be indices of the schools that the greedy algorithm picks. So we don't know these yet. Assume that for every two elements inside of this array over here, the element that comes before the next element will be smaller. So element number 1 will be smaller than element number 2, element number 2 will be smaller than element number 3, so on and so forth. Then let's have another element, let's have another array, J1, 2, 3, and these will be the indices of a school that an optimal algorithm picks. So assume that for the same, for each element in this array, the previous element will be smaller than the next element. So first is smaller than second, second smaller than third, so on and so forth. And let's look at both algorithms, arrays. The greedy array, the sum of all of the elements in the greedy array will be lesser than or equal to n. Why is that so? Because n is the number of lunchboxes that you have, and you cannot give out more than what you have, right? So it will have to be lesser than or equal to n. For the optimal algorithm, that's also the case. So since we know that for each element in greedy, it will be less than or equal to the optimal element chosen by like the optimal algorithm, it can be shown that this greedy algorithm is, what does this mean? Oh, the greedy algorithm will be at least as good as the optimal algorithm. Yeah, I think that's what this means. So yeah, so essentially what all of this means is that if you just sort the schools, if you just sort the lunchbox, the number of lunchboxes that each school needs in ascending order, you can give each school the lowest amount of food possible so that you can give more schools food. Okay. I feel like that wasn't explained very well. Does anyone have any questions or want me to explain in a like using a different way? Uh, okay, I'll just assume that you all understood. Okay, so some more greedy problems over here. So you can try lunchbox potato salad, GSS paint Chinese restaurant. If you want more difficult problems, you can also use these for best place competition, cat lunch, and car park. Okay. Sriram, do we want to do these problems first, then go on to BSTA? Or like we just okay. All right. So yeah, we'll just do lunchbox, potato salad, GSS paint, Chinese, and restaurant. Okay. So let me just send that into chat. Okay. 10 minutes each. Wait, that's 1 hour. No lah, no lah. Okay, y'all don't have to do all of the questions now. Let's just say try and do 2 questions minimum. We'll give y'all 20 minutes, I guess. So at 2:51. Also, Alwyn, what he asked, why are there 300 test cases for minimum? Uh, I don't know. Like the guy who did it must have been high to put 300 test cases. Yeah. Oh yeah, it might be to kill Python or something. I don't know. Like I think minimum was made by an RI guy, right? Okay. Never mind. Yeah, RI's trainers love to kill Python for some reason. Uh ha ha ha. Yeah. 4 MB memory limit. That's insane. Okay. So yeah, come back at 2:50. Try and do at least 2 of the questions that I stated in chat. Yeah, and try and use greedy algorithm. If you don't understand, you can just DM the trainers, or you can also just like ask in this chat. We don't mind. Yeah, give us something to do. Okay. Okay, so one guy. Yeah, that's a good start. That's a good start. Who's done at least one problem? Okay, so two people. Sure. Yeah, okay. So now that we're done with greedy, we're gonna move on to binary search, and Kai-Ting will be taking over from here.
I assume you guys can see, so hello. Okay, let's just say I'm gonna think of a number between 1 and 100, and you're gonna try and guess what that number is. And every time you make a guess, I'll tell you if it's too high, too low, or like the correct number. So what strategy are you guys gonna try to guess in the least number of guesses possible? Does anyone want to try?
Keep halving the number.
Okay, yeah, that's correct, and that's basically what binary search is. And since we guess half of the number every time, then every guess we make actually cuts the number of possible answers into half. So the time complexity of this will therefore be O log base 2n. So let's say we have an array and we want to find the index of a value in the time complexity we said just now. So in this case, we want to find 3. So we guess in the middle, then since it's too big, we just guess like the middle of the lower half, and we just continue until we got it. Okay, so keep in mind here, very important, the array has to be sorted, because if the array isn't sorted, let's say we can just guess a random number here, like let's say 5, but we can't say for sure that like 3 is not going to be here, because the numbers here could be smaller than 5 as well. So this one you guys can just watch. You can see there's a very big speed difference. And so here's like the sample code now, which is basically what we just talked about. You guys can reference this later. But actually you don't really need that if you just want to binary search on an array, because C++ has built-in functions, which is lower bound and upper bound. So what these things do is they return an iterator, if you know what it is, to either the first element greater than or equal to, or the first element greater than whatever value you're trying to find. This is just like more syntax stuff. Like the main two important things here is the actual element, the index to the element. But this kind of stuff, you should just take note of it, because I'm also like not really gonna bother explaining exactly how it works. And you can actually binary search on a lot of things, including sets and maps. The syntax is slightly different here. Instead of lower bound and then the array plus the length, then the target is just whatever like variable name your thing is set to, dot lower bound slash upper bound to the target. And so after this, you can do like quite a similar thing to this, where you put the asterisk in front if you want the actual element, or if you want the which index it is. Oops, you just minus this. But in the case of set and map, I believe that this should be your set dot begin. Okay, so when I say you can binary search on anything, I mean you can binary search on anything. So in this case, this problem is a cube root, in which we give you a number and we want you to find the cube root of a number. So what we can actually do here, other than just like the built-in C++ function, is we can kind of make a guess, and then that guess is either going to be too high or too low, and like that we can kind of split our answer range into half, that one is correct and one is confirmed wrong. Okay, so let's get on to like a more complicated problem. Okay, so there's some number of boxes of iPads arranged in a row, and each box has a certain number of iPads. So you want to distribute these to a certain number of people, and each person can only receive a consecutive range of boxes, and like they must take everything from a box they are taking. So what you want to do is you just want to reduce the max number of iPads each person is getting. So for example, like this, is there's 9 boxes and 3 people, we can distribute the iPads like this, and you can see here the number we actually get is 17. That's the maximum number of iPads that one person is getting. So yeah. But we don't really know how to get to this answer. So what we're gonna do is you can actually like binary search for this if we actually flip what we know and what we're trying to find out. So with the assumption that each person gets a certain number of iPads at most, so we can actually see if it's possible to distribute the number of boxes this way. So what this means is that it's obviously possible if you have an infinite number of people. So we want to find the amount of people we need to distribute the iPads in such a way that only each person gets at most a certain number. So after this, we can just check whether how many people we need to achieve this maximum. And we can just use greedy for this lah. So obviously each person should just take as many as they can until they stop. So given that our number here is, for example, 15, we take until here, and then we find that if we take the next one, it will be too big. So we just like assume the second person takes that, and we just keep going. And what we actually find out is that we actually need 4 people to allow the maximum number of iPads we taken to be 15. But if in our sample test case earlier, we see that we only have 3 people, so this 15 is actually not possible. So that means that the maximum number actually has to be higher, because we can't go lower than 15. The sample, because you can see it's quite the same as last time. You have a lower bound and an upper bound, and then a while loop. And then to calculate the in mid is like our guess, which is like I said, in the middle. Then after that, we just check if the thing's okay. We just check if the thing is valid. And if it's valid, then we can say like our lower bound is the middle, and if it's like too big, you can just say that we can just set the upper bound as the middle. But like, why can we actually binary search this? Because our answer is actually this thing called monotonic. So as you can see here, if you take like any random position, like let's say here, and we see no, then like any answer below 15 is also a no. And if you take any like yes, any answer above the yes is also another yes. So because of this, we can just binary search on this. Yeah, and so what we want to do here is we actually want to minimize the value that it has a yes here. So what we can do is we can actually just binary search for it. So we're actually binary searching for this thing that is a yes here and a no to the left. So that will be our minimum. Okay, so summary. there's two things you need for B-star to work, and the first is monotonicity, which means that for every guess you can split our answer into like a confirmed yes range or a confirmed no range. And then we also need a way to check whether our guess is actually like possible, like yes or no. Okay, our sample code. You can read that later. Okay, our problems. So I think you guys should just go do the problems now.
Okay. I think array find and cube root 10 minutes each is okay, but summit might be a bit more difficult lah. Let me see. Okay, summit is about as difficult as squids or forensic. But yeah, it is still a bit difficult. Let's just say, okay, 10 minutes each. Okay, let's just say 340. Try and do all the questions, but do array find and cube root first, because those are easier. If you've already done them or you finish faster, then you can try and do summit. Okay. Yes, go do problems. And tell us if you need help.
Hello.
So wait, just
Oh, no. I'm just asking which technique should you use to answer this question.
Oh, okay. Just use okay. First you sort the array, then you use binary search to like check if it's bigger. So what you do is you go to the middle, check if it's compared to the middle. If it's bigger, then you go to the left or right. Right.
Okay.
And if it's smaller, then you go left. Yeah, that's it.
Okay. So as you all can see, Om is very smart because he answered the question correctly. So yeah, I'll just explain what he said. What we need to do is we need to do binary search. Oh, and we also need to sort the array. So what we do is we have the array, we sort it, and we are given a number x. How do we know how many numbers are less than x? Well, the easiest way to do this would probably be to, how do I say this? We use binary search to find a number that is greater than or equal to x inside of the array, right? When we find that number, we see first we can use its index in order to find out how many numbers are lesser than it. Similarly, we can also use binary search to find a number that is at least greater than x inside of the array. And using that index, we can find out how many numbers are greater than x inside of the array. However, we don't actually need to code out binary search over here. What do I mean by that? Well, if you all remembered, just now, how come I cannot share screen? Okay, just now we went through something called lower bound and upper bound. So what is lower bound and upper bound? If y'all don't remember, lower bound essentially gives you an iterator inside of the array, which is, how do I say this? It's the first position in the array where you can insert this number x, and it will not it will not affect the manner in which the array is sorted. Essentially, it'll point you to the first number inside of the array, which is greater than or equal to the number x. Upper bound will point you to the first number that is greater than x. Yeah, I'm pretty sure that's the definition. Okay, so let's just go through the solution on how to code this. Firstly, we have our main function. You have the integer L, Q, and X. L is the length of the array. Q is how many queries we are doing. X is just a placeholder for now. And we use a vector to store the array. Okay, this over here is to input all of the numbers in the array into the vector. I don't know why I call it ARR. It would probably have been better to call it .v, but who cares? And then we sort the vector using .begin and .end. After that, we see in our number of queries. Next, we initialize two variables, s and g. S is how many numbers are lesser than x. G is how many numbers are greater than x. And we do this for each query. Integer y. So we want to know how many numbers are lesser than y, how many numbers are greater than y. How do we do that? So first we use lower bound to check how many are lesser than y. Lower bound on the array, array.begin, array.end, and we check for the variable y, since that's a query. This will point us towards the first element in the array that is lesser than or equal to y. But we have to note that this right here, lower bound, will return us an iterator, not the index, not the value. It returns us an iterator. So how can we convert this iterator into an index? Well, what we can do is actually just use arithmetic minus array.begin. Why does this work? Because this iterator, it points to something in the array, the vector, which is called ARR. I'll just call it an array. It points to something in the array. And when you minus a pointer to an element in an array, you minus the starting point of that vector / array, it will just return you the index. Because Okay, if you have the starting pointer of an array or vector, in this case it's dot begin for a vector, each element subsequent to that will be +1, +2, +3, so on, like using math. So by minusing the starting pointer of the vector, we can just get the index. And we don't have to -1 or +1 to this, even though it's the index, because this is, even though this includes the number that is equal to or greater than y, it's still true that this is like 0 index, so we don't have to -1 off of the iterator, which includes the number that's greater than y or equal to y. Okay, next for greater than. First, we take the number of variables in the array, because we need that in order to calculate how many elements are greater than it. Then we use upper bound. Upper bound, okay, wait. Okay, it actually has a definition here. An iterator pointing to the first element greater than the value. Yes, the first element greater than the value. So we want to know how many elements are greater than y, right? What we can do is array upper bound on the array.begin, array.end, check for value y. It'll point us towards the first variable that is greater than y. And then we can do the same trick minus array.begin in order to get its index. After we do that, we have the index. We can take L minus that index in order to know how many numbers are greater than y in the array. Because, yeah, L is how many numbers are in the array. So that's what we do. And then we see out the answer this way, because this is the question format. And that's that. Using pointers may be a bit confusing. So if any of you all want to clarify anything, please ask now. Okay. If nothing else, then we'll go on to cube root.
Okay, if I'm not mistaken, I briefly skimmed this through just now. Okay, so I mean the question is quite simple. You just give it a number and you just want to print the cube root, and you actually have to handle multiple test cases. So they're gonna give you a number of test cases, and then they're just gonna give you each test case, and you just have to see out each one a new line. So remember, like, the two things about that must be there for binary search to be used: the monotonicity and like a way to check the answer. So the way to check the answer is very simple. We just have a guess, and then we cube the guess, and then we see whether it's like too big or too small or just right. And for monotonicity, you see that, like, obviously for any guess we make, like if we guess higher, like that number cube is obviously gonna be higher. Okay, so first we just get the number of test cases, then we iterate for every test case. Oh, you can't see this, sorry. Okay, yeah, here. Then for every test case, with number x, we see the so we need the lower bound and the upper bound to start with. In this case, I'll just use 0 and 1 is 6, since 0 is the lowest it can be and 10 to the power 6 is the highest it can be, since the numbers can only go up to 10 power 18, which means the cube root is 10 power 6. So while L is less than H minus, we make a guess. Then to check the guess, we cube it and we check if it's equivalent to the thing or not. So let's say our guess C is too big, then our new upper bound is the middle, and otherwise our low is the middle. So it's CRL. So if this should work. Oh, whoops. I forgot. Let's grab back up. Yeah, there you go. Okay, so like because you see this, it's not really an array, right? So there's something you need to be careful of when you're coding this manual binary search. You need to make sure this while loop actually breaks with this condition. And like depending on what you are doing here, you need to see out the correct thing, whether it's L or H. I mean, I believe technically the bounds of this question, I think you can just make an array and it's also possible, but I mean like especially for B star, you can't always use an array, so you need to actually learn how to code all this, even though the lower bound and upper bound exist. Okay, so now I'll pass the time on and they'll talk about Summit.
Wait, you can actually just use the cube root function for this question, I think.
Yeah, you can, but that's cheating.
Oh, wait, I didn't use binary search. Okay, never mind. Do it properly.
No, I used that originally, then I later went to November course and they forced me to use the cube. The freaking yeah. Okay, moving on.
Shriram, you know we can't hear you, right?
Oh man, you should have just let him keep talking, bro.
All right. Basically, when I was yapping to myself, what I was yapping to myself was that you can actually use Cuberoot's code for this. You just need to change like 5 to 6 lines. It's gonna work. So the problem here requires you. Okay, the problem here basically is that you're trying to climb a mountain of m meters, and like on the first day you climb k meters, and on subsequent days you are able to only climb like an additional k over d meters, then k over d times d plus 1. Yeah, this funny function here lah. This is a general function as the number of days go by. So
Sure, you're muted.
still eh so okay, what's going on? It's crazy. Wait. Can you hear me now? I think my mic is actually wonky. Wait, hello, can you hear me? Wait.
Bro, I think you might wanna like
Oh yeah, fair enough. Hello.
Yeah. Can hear now.
But I hate technology. Technology sucks. Okay. Bad technology. Okay. I have to do this again. Okay. Basically, right, the problem requires you to climb. It requires you to climb a mountain of m meters. On the first day, you're able to climb k meters, and on subsequent days, you can only climb k over d, then k over d times d plus 1, and so on. And like, it's represented by this function. Yeah. So basically, the general idea is that you're able to climb k meters on the first day, but on subsequent days, number of meters you're able to climb it decreases until one point it will eventually reach 0. And the moment that the floor of this function reaches 0, you are no longer able to climb further. So you obviously wanna reach the summit of the mountain lah, obviously. So you want to know the minimum k such that you're able to climb m meters. Now, if k was like infinity, right, it doesn't matter. But there's no point of having a question if that's the case lah. So we want to find the minimum k such that we are able to climb m meters. Now let's look at the constraints. Since it's a binary search problem, as we have established earlier on, d is super small, 15. This basically means it does not even matter. D is so small, it doesn't even matter. You can just brute force this function here. In the code, you can just brute force this function, as I will show you later. And it really won't matter for TLE. It won't TLE. Your main concern is this one, 10 to the power of 15. M can be between 1 and 10 to the power of 15. Obviously, like ON doesn't work, right? Or ON clearly won't work for this. Since, unless you want to use super advanced math, there's no point of you doing it. You need to conserve your brain cells. So therefore, we simply binary search the answer. Like we literally binary search k, just like Cuberoot. So I'm too lazy to like code it out. I did this yesterday because like apparently I haven't done it before. So okay. So yeah, C in M and D. Oh yeah, wait. I forgot to show what D actually was. My bad. D is just a constant really. D is just a constant in the input. The second number is D. And it depends on the input. Second day could be k over 2 if d equals to 2. If d equals to 15, second day would be k over 15. This would be k over 15 times 16. This would be k over 15 times 16 times 17, blah, 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 blah. So you get the point. All right, now let's actually go to the code. Ignore all of this. I accidentally forgot to delete this. Okay. So yeah, actually I don't think you need to use unsigned long long, but I just want to play safe. So just use unsigned long long as I defined it over here. Then just like Cuberoot, while high minus low equals greater than 1. Again, high equals to m plus 1 and low equals to 0. Obviously you can't climb 0 meters down. So we just keep it like that. So we find the middle just like this. And now what's different from Cuberoot is basically these next few lines of code. I'll try to stick them. Current or CURR is basically the current elevation you're at. Like let's say, right, the K we choose, actually should open this in tab, yeah. let's just say let's just say the binary search, right? The k we choose is like 15 or something, for example. Then like on the first day you will climb 15 meters because you climb k on the first day, right? CD is CD is basically this denominator over here. You see this here? Yeah, this denominator. That's what CD is. And B is just the like B is just like this guy here. Instead of like calculating this, instead of calculating a denominator and over again, what I do is that first I have like, let's say D equals 2. First I have 2, then I multiply by 3. I save the number, then I multiply by 4, and so on. I just keep a running multiplication, if you get what I mean. Instead of like calculating it over and over again. This one, like, it just makes my code look simpler and easier to understand. So while your current elevation is smaller than m, and mid divided by CD is not equals to 0. Because remember, mid is k, and CD is the denominator. As you know, right, eventually this function is going to return 0 once when it's floored. So and when you use the divide in C++, it automatically floors it. So that's something you don't have to worry about. So when you have, so we keep on we keep on climbing until we either this hits 0 or we already reach the top of the mountain. So current elevation plus k over plus the function k over that funny denominator. Then we increment b. Then I multiply the denominator by b, as you can see from this function here, because I multiply one more than the previous b. You can see from here. So we just keep on doing this, and once it hits 0, once we reach the summit, if we successfully reach the summit, then we know that this k is high enough such that we're able to reach the summit. This k could be either the answer, or there could be a smaller k that allows us to reach the summit. But if the elevation we have reached is lower than m, that means using this k, aka the mid, we are unable to reach the summit. And so the answer cannot be lower than this mid. So therefore we set low to mid. So we keep on doing this until high minus low is greater than 1. And since high stores the last successful k, because low stores like low stores like the highest unsuccessful k, this high stores the lowest successful k, and we want the lowest successful k, right? Minimum k that allows us to reach the mountain. So therefore we put high. Any questions? If you have any questions, just clarify or DM the trainers. We'll be happy to help. Okay. I will assume there's no other questions. So let's just go to the last and final part of this. And first, let me charge my laptop. If not, it's gonna die. Sorry, give me a minute.
Wait, it's already 4:10. Uh, Technically we're supposed to let you off at 4.
Wait, does it end at 4 or 4:30?
I'm pretty sure it ends at 4, right?
Sports.
Okay.
Mr.
How about y'all can leave, but we'll just go through like whatever we have to do right now. But if you wanna leave, you can leave lah. We're not gonna stop you.
Yeah, okay. There's some practice questions for you to do, but we won't wait for you to just do it on your own after the lesson. So just go through this last part. Anyway, sliding window is not the most complicated. So yeah. So
Wait. How is sliding window also known as binary search?
I also know why this is here. You know what? Let me just delete this. Okay. That some goofy Google clown put it there. Okay.
Is
So
that
yeah,
Bujakai? Is that Potato Man?
I don't think so.
No, I did not actually put that in. Sadly.
Sadly. I
Why
sliding
won't-
window. So
Wait.
just the inspiration for this flamethrower on codebreaker. Basically, the abridged statement is find a contiguous subsequence with length of k such that the sum of every element in the sequence is maximized. Just test every possible consecutive sequence. No lah, that's way too slow. You're going to TLE. Like imagine your k is very large, like 6. If your n is 15, right? let's say your k like very large, like 1,000, and your n is like 100,000. We're going to keep on going through, right? If you're just going to go through the first 1,000 elements, then go to the next 1,000 elements, you're going to like that. So slide the window. How do you slide a window? We weren't joking. It's literally a sliding window. Look at this. V. Sliding window. Just push it. Okay, now how does it actually work? Okay. So let's just say, okay. Oh my god. So let S be equals to 0, your starting index of the array. That something is, okay, this is very badly worded, but something is the size of your window. You know what? Let me just like make it clearer for future generations. Yeah, size of window. So that's where you initialize your sliding window. Sliding window is nothing much, but you just going through the array, so you don't need to be like worried about it. So while E, that means the end of your window, is not equals to n. That means you're not at the end of the array yet. What you do is you add the current E, so you add the current end of the sliding window, and you subtract the beginning of the sliding window. So you get this, and then you increases. Then you increment the indexes, S and E. That's how you're sliding the window. This is where you slide the window. But actually, this isn't the most clear one. I think this is a better way of implementation rather than that one. This one makes a lot more sense. No, this is the most clear code actually. Screw that, honestly. So you should. I think this is the code for flamethrower. I'm not sure actually, but int n window size. This is just the array, your typical array. This is the sum of the window. This is the sum of the window, the total sum of the window. Yeah, you input that. This is basically the k in flamethrower. Yeah, from I0 to IN, as usual, input the array, but this one is a sliding window. While I is still less than the window size, you add AI to sum. So this is where you're finding the sum of the first window. For example, if the sliding window size was 2, right, you're basically doing this. You're finding the sum of this guy and this guy. That's what you're doing. So then int, and then this one will store the answer, max. Actually, wait, why is it max? Let's do it. Don't put max in your code, because max, the compiler will think you're talking about the function max, which is obviously wrong. So yeah, don't use max. Use ans. Okay, now that's done. For int I equals to window size, this makes I start where you left off for your window. So if window is from, so let's just say k equals to 3, right? That means you have A0, A1, A2 inside. Now you want to start from I equals to 3. So what do? Sum minus equals sum minus equals AI minus window size. What you're doing here is that you're removing the first element in the window. Because now you're sliding the window towards the right. So now you're removing the first element that was in the window. So that means if we started the window at 0, that means here you're removing A0. So sum minus equals A0. And at the same time, because we are moving the window towards the right, we are adding A3. If the window size was 3, that means we're adding the third element of A while subtracting the 0th element of A. And if sum is greater than answer, we update answer to have sum, because we want to find the maximum contiguous subsequence. But actually, there's a better piece of code. We usually use this. This is why you shouldn't use the word max. Max is a standard function in C++. Yeah. Doing this will also automatically will also do the same thing. It will change the answer to the maximum sum. And once you're done with that, yeah, see out answer. So what do these two lines do? Let's say you started here, your sum now is 7. Now you slide here. Since the window size is 2 in this scenario, you minus A0, so 7 minus 5 equals to 2. And you add A2, because you just added this into your window. So 2 plus 6, 8. So the sum of these two elements are 8. So as you can see, right, sliding across the, so as you can see, right, calculating the sum of each window has been reduced from OK to O1. So that's like very that's a very big reduction in time actually. So yeah, we have this again. We start a window, we decrease what's not there and we add what's like newly added, as you can see from this visualization. So our maximum sum is 2020. Sorry, our maximum sum is 22, and as you can see, we just had one pass through the entire array. So therefore, our time complexity is O n, not O n k. What if our window size is not constant? You can actually binary search the window size. Although actually I've never done this before, so like I also don't know how this works. Nah, okay, that's confusing stuff. Let's not look at it. Okay, we'll just go through lineup and should be it. In an array of n cows, find the minimum possible distance between the start cow and the end cow of a contiguous in sequence that contains at least one cow of each type. So here's the thing, right? If a range from left to right contains at least one cow of each type, then so does L minus 1, comma R and L, comma R plus 1. Why is that the case? Because these two ranges, these both include the range L, comma R, right? So that's why this statement holds true. Therefore, monotonicity. Familiar? Yeah, this is from binary search. But we're actually not going to do that. So let bi be the minimum cost of photograph that ends at cow I. And initialize all bi to a very big number. Doesn't have to be 9, 18. Just like put something that's bigger than the constraints given to you. We use a sliding window to compute the whole bi. So we use two pointers left and right. Yeah, so basically what you should do is you should have two variables called L and R, set both to 0, and we fix the right pointer and try to slide the left pointer to the right as much as possible for the position of the right pointer, then slide the right pointer by 1. So basically like we move right to a certain index, we keep on increasing left by 1 until it reaches right, and until as much as possible for that position of the right pointer, then we slide the right pointer again. So I'll just show it through code. No, I'll just show it to you. I mean, it's very hard to say it like that. So let's say here are the cow positions, and here are the cow's type. So again, we need to use a set to maintain this. So here we only have one element, so we can continue going on. Here we only still have only one element, so we can continue going on. We have 2 out of the 3. Now we have 3. We have all of the cows. So as you can see, right, we have this, right? So this is our first window. So 25 minus 15 is our provisional answer. But obviously we want to minimize this difference. That's the answer. That's the whole point of the question, right? So because this window works, we now delete the starting one. As you can see now, we deleted the starting one. And we move on to the next number. But as you can see, right, once we deleted it, right, you can notice that we still have 3 numbers. We still have all 3 numbers in our set. So therefore, we can update the answer. So it's not 25 minus 15 anymore, it's 25 minus 20. That's the smallest window we have so far. So let's continue. Again, delete, because we've got a good window. As you can see now, we only have 2 unique numbers in our set. Yeah, we only have 2 unique numbers in our set. There's a typo here, sorry. So when we don't have a complete set, then we continue going towards the right again. Here we have another set with 3 elements because we have 3 inside. And yeah, 4. This is therefore the smallest. So yeah, once again, quote here. Actually, I don't use lower bound, you can just use fine. So yeah, as you can see here, right, it's a set and multi-set. While the set size is not equivalent to size 1, if I'm not wrong, it's the number of unique elements found in the array here. It's the number of unique types, total number of unique types. So while the set size is still not equal to 1, you like oh no, what am I saying? No, you keep on adding it enough, and then like once you realize that your set size is equivalent to size 1, you just erase the the left of this. That's what this ms.erase does. It erases the left from here to here. That's what it does. And then like yeah, I mean the code's kind of self-explanatory honestly. Okay, again, if you have any questions about this, just like go through. Again, I don't really want to hold you all like back for a long time. We are like 22 minutes over time, so like I think you should go sleep. I guess I don't know. You can try catch fight if you're free. Yeah, I think we're done. So if you have any questions, feel free to ask any of the trainers. DM us. You can even open a ticket if you want to. And yeah, thank you so much for attending and goodbye. Hello, Jakai.
Hello.
Hello.
You're still live.
Yeah,
You're still
it's
live.
still alive. Swagat, are you alive? Is Swagat remotely alive?
It's so funny listening to the stream.
Yes.
Can we like turn on like people are gonna watch this and just gonna think like what the is going on?
Wait, is this still live?
Oh yeah. Probably like it's probably like unlive it. Give me a
Yes, it is still live.